Well, I think we can start. So welcome. Welcome to the 10th edition of the SBAI workshop, Synthetic Biology and Artificial Intelligence, which this year is dedicated to self-organization in nano and electromechanical robots, the transition towards the robosphere. I'm Luisa Damiano, I'm one of the organizers. Other organizers are Antonio Flores, who is here with us today. Then there is Yutetsu Kuruma, who could not reach us, but Andrea Rolli and Pasquale Stano are online from Italy, and they say hello. We wanted to dedicate a few minutes to a brief introduction to the workshop, focusing on the notion of robosphere, which is the notion at the center of of this edition of the workshop, and at the center of the first talk that we will have today. So our bet is the notion of robosphere will bring a profound transformation in how we think today robotic technologies. Indeed, this notion has a long history, was introduced by Umberto Maturana, one of the two ideators of the theory of autopoiesis in the late 90s. Is not one of the notion for which Maturana is famous, but introduced also this notion. And then a series of authors reconceptualized this notion. And to our knowledge, the last is Antonio, who dedicated his PhD to the notion of robosphere, also to the notion of robosphere, to a conceptualization of this notion that intends to transform the way in which we see robotic technologies in regard to sustainability. Indeed, at the center of our workshop, there is the idea that robots are becoming more and more interconnected. On one side, among each other. On the other side, with us, with our social systems, with our natural ecosystem, with other technological ecosystems that are not robotic. So the idea that we are trying to develop, our hypothesis, is that we have a twofold self-organizing process related to robots. So robots are interconnecting with each other, as I said, through different scales. That's why we are focusing on chemical robots, but also on electromechanical robots, and through different fields. Industrial robotics, medical robotics, space robotics, social robotics. On the other side, the second aspect of this process is the interrelation that these robots are realizing with us, establishing hybrid socio-technical systems and hybrid techno-natural systems and so on. So what we call robosphere is the self-organizing network that is emerging from these processes of interconnection. And our hypothesis is also that this self-organizing network shares some aspects with self-organizing systems or networks as we already know them. In particular, some degrees of autonomous adaptation, which involve also processes of self-regulation, which from the point of view of the autonomy systematization of cognition means also some forms of distributed cognition. Because in an autonomous perspective, cognition is the association to perturbation to a system of patterns of self-regulation. So what we propose is to think the robosphere as a new sphere within a system, an hyper-complex system that we can address through the Gaia theory by Lovelock and Margolis. So a new Gaian force that in a hyper-complex system of Earth is interacting through self-regulation processes with the technosphere, the anthroposphere, the biosphere, and the global ecosystem. So in particular, in this workshop, we will focus, as the title says, on chemical nanorobots, but also on electromechanical robots and their dynamics of interconnection between them and with anthroposocial system, natural system, technological systems. We think that it is very important in these years to focus on the notion of robosphere and this systemic view of robotic technologies and their interaction with us and with other systems, with regard to sustainability. We think that the classical approach to social and ecological sustainability to robotics is based on a reductionistic view, on an atomistic view, that bring us to consider robots as separable tools, separable from other robotic systems, from anthroposocial systems, and so on. But we think that we need now, in this moment of growing interconnection of robotic technologies with other systems, we need to see the interconnections and to try to understand how these interconnections work to be able to address the challenges that this interconnection will bring to social and to ecological sustainability. So our challenge is this. If we understand these interdependencies, then maybe we can act in the direction of bringing a balance between robotic evolution, human evolution, and natural evolution, and the protection of the global ecosystem. So the main objectives of our workshop are these. Of course, our objectives now, I will read them, but that cannot be reached with one workshop. So we will also have a special issue, but more than everything, we hope that this moment is the starting point of a dialogue about these topics. So the objectives that we would like to propose to this forum today for the future, for future research on the robosphere, are the examination of self-organization processes involving robots, the analysis of multi-scales and hybrid interconnections and interaction between robots and other systems, issues related to sustainability, and the construction of a roadmap to address all these issues. So the main aspects that we will try to cover today also through the talks are these: parallels between robotic systems and biological, more in general, natural systems, multi-scaled and hybrid coordination, social and ecological impacts of these processes that we are trying to conceptualize as self-organizing processes, sustainable development of robotic technology, ethical framework to support this sustainable development, and different modeling approaches. So the workshop is divided into parts. We scheduled 4 talks for the first part, but unfortunately one of our speakers, Agen Lehmann, is here in Kyoto, but got the flu, so will not be able to give his talk, which is very unfortunate, but means that we can give to the other speaker a few minutes more and also to the discussion a few minutes more. So we will have Antonio Fleres, then Fernando Rodriguez Vergara, and then Shinichiro Nomura. Nomura-san will participate online, then a break between 3:30 and 4 corresponding to the coffee break. And then other 4 talks. Francesco Bianchini will participate online. Rebecca Mannocci is here. Jean-Sian Venture, she will participate online. And then Vipra Chopra, who will participate online. And then we hope to have time for discussion. So without further ado, I introduce Antonio Fleres. As I said, Antonio developed his PhD research on the robosphere, also on the robosphere, reconceptualizing this notion in order to address issues of sustainability related to robotics.
Thank you, Luisa. Okay, thank you. Okay. Okay, are my slides visible from home? Yeah. Okay. I think I need the adapter.
Is it stable? No, ancora. Aspetta, aspetta, ok.
Okay, perfect. There is a bit of echo. Mhm. Yeah. Uh, on my laptop. It's already closed. Is it working? It's already muted. What if I
Then, maybe you can just try to activate your own microphone. In that way, we can just hold that.
Mhm. Okay, can you hear me from home?
Yes, all good.
Okay. So my presentation. Mhm. Okay, is it working? Again. Is it possible to just turn a little bit down the volume here?
They cannot hear.
Oh, I mean, later for the question, but we can put the microphone to the speaker. But they're very pretty.
Can you hear me from home?
Yes.
Okay.
No, yeah, I think the problem is that that thanks to not being connected to the projector, then the projector picks up your the microphone of your computer. Yeah.
The problem is when I start the presentation because the microphone is
Yeah,
yeah.
I see.
Projector does not.
And starts there.
Video. A solution?
Maybe
Just
you can share on the phone.
Or when you share the mic options, like option nine. There is like a whole app.
Face the presentation.
Non puoi mandarmi a spiegare.
No, perché non ho. Okay. So I have to.
Is sharing? Okay.
Bisogna. Andiamo a condividerlo su Zoom.
I can hear pretty well, but I can't hear. You can hear?
You have to press back on meeting, like on the previous screen.
Screen.
Where it's hidden behind the camera, like the orange button. Yeah.
Back on meeting.
Then-
Okay. Sure.
Now you can start.
Okay, it seems we are sorted. Yeah, maybe. Sorry for the inconvenience. Could you hear me from home?
Yes, we can hear you.
Okay. Okay. So I'll try to be very fast with this. Okay. So my talk is called "What is the Robosphere? An Epistemological Perspective," and here have just an overview of my presentation. Is divided in 4 sessions. So I will introduce briefly Robosphere. What is yeah. So, and I mean, this is just an overview, and introducing the robosphere. Basically, nowadays we have it's just behind. I mean, in front of us, robotics is a very important and prominent domain, which is just impacting on our technological development, and it's extending across like our industrial production, healthcare, and mobility, agriculture, and domestic environment. So basically, robotic systems are becoming a way how we human mediate with like a lot of different activities, and it's even because the rise of social robotics, it can be able to impact human sociability, and this means robots are walking into this new social world, human social world. So they are able to interact with us socially. So basically, this field is evolving from isolated standalone system into interconnected adaptive system. Basically, James Lovelock, as Luisa already mentioned, is in her presentation. He was envisioning as the future of Gaia the emergence of. I mean, in future, obviously, the emergence of an electric biosphere composed by cyborgs. So, and when he was describing those cyborgs, basically he was depicting artificial agents, robots. And nowadays we are probably facing a kind of embryonic robosphere, and I have listed some hints of this, and they are like Internet of Robotic Things, domotics and robotics, operational ecologies, and cyber-physical social systems. And I'll be fast here. I don't. I cannot go into detail. So we have like Internet of Robotic Things, which is the results of the merge from robotics and Internet of Things. And then we have domotics, which is like the robotization of the domestic environment together with robotics, which is the robotization of the public space in, for example, smart cities. And both those domains involve the network robotic systems, which are able to reshape the way how we conceive our daily space, basically. And then we have even operational ecologies, so which are basically complex robotics systems capable of interacting with natural ecosystems. And so, for example, we have here some application, some example of application, like, for example, for species conservation or automated pollination or climate modification as cloud seeding. And then another hint is like the rise of cyber physical social systems. In general, those systems are are the result of the integration of physical and digital compounds to, for example, control infrastructures. And some application of these are like, for example, smart grids and autonomous vehicle. And now they are able, for example, using specialized interfaces, so like social robots, they are able to connect with the human social environment. And all of these are connected each other. There is an element which is common to all those examples, which is this trend, which Nosokov called networkism. So it's this tendency of creating systems which are composed by multiple artificial agents, and they are decentered. So, and this is represent basically the foundation where this embryo of robosphere can be grounded. So the use of the term robosphere, basically, I have found three scholars which have used this term. So first of all, Umberto Maturana in 1999, and then Silvano Colombano in 2003, and Malasela John Lamola in 2022. The first of all was the scholar Umberto Maturana, who used the term to describe a potential future geological era. So according to him, there was three main planetary eras: the biosphere, which started basically with the appearance of life, basically. Then there was the homosphere, which was the emergence of the human world. So human language, society, and technology. And then at the end, he was envisioned the future, the evolution of homosphere, which he called robosphere. So which was the era dominated by technology and machine over humans, and where everything was basically an operation followed the strict rules. And so here he made just a distinction between robots and living systems. So, for example, he was saying, okay, robots are basically assembled, and they don't, they are not the result of a historical evolution, and they are really designed to operate in specific circumstances. And on the contrary, living systems, they have an evolution, so they are historically based, basically, and they are always at the right place. They are always in the right circumstances to operate. And so basically, Maturana perspective on robosphere could be kind of negative, because he's using this term in a negative way to depict the degradation of human sociability. And then we have Silvano Colombano's robosphere. So basically, he used this term to describe a self-sustaining robotic ecology designed to space exploration, in particular for Mars exploration. So he took inspiration by the project Biosphere 2, And the key feature of is robosphere is to be able to be self-maintained and self-repair. And so basically his robosphere is ecological robotic ecology with modular robots able to self-repair. And so it is even able to just energy production, and it can construct and repair shelter for protecting robots. And he's even making a kind of envision about the future of robosphere, where basically the robosphere is able to construct, to build an environment to sustain human life on other planets, like for example Mars. And so he's also considering the robosphere on different scales, from nano to macro, and he's envisioned the capability of robosphere of self-organizing itself and self-replicate itself, and together co-evolve with the anthroposphere, the humans, with and within. And then we have the Lamola definition. So Lamola basically has used the term to conceptualize from a post-phenomenological perspective social cyber-physical systems. So in his conceptualization, basically human and robots are equal, and he borrowed a term from Bruno Latour, and the term is actants. So humans and robots are actants together inside the robosphere. And he has even used a new term, which is, he has coined this new term, which is called humanoidic robots. So humanoidic robots basically are robots which cannot be considered humanoid because they don't have a human shape, but they are able to communicate with human using the same kind of sociality. And basically those robots, those humanoidic, are able to give in the feeling of being with someone. So, and for example, some example would be Paro or Spot. And so basically for him, robosphere emerged as a new technological homeworld. So it's a human-centered environment able to generate new meaning and experience. And then let's move to my reconceptualization. So I propose a reconceptualization trying to align the term robosphere with complex system theory, trying to generate a new perspective on robotics able to fit the global planetary systems, and even with the aim to create a definition which can fit the sustainability needs. And so here, I'll go fast. We have the 6 principles of theory of complex systems: feedback, hierarchy, nonlinearity, emergence, network, and self-organization. And I have used all of them in my definition to better describe how robosphere work. And this is the definition I just came out. So I'll just illustrate step by step. So step 1. The robosphere can be defined as a totality of integrative ecologies of humans and robotic agents, interconnected and or interacting across different scale from nano to macro within the planetary system. So here the interesting part is like, which the robosphere is the sum of all the integrative ecologies of human and robotic agent. So I have took this term integrative ecologies from my professor, Luisa Damiano. And it's referring to mixed ecosystem composed by human and robots, basically. And they are interconnected in many ways, socially and technologically. And and we are considering in this definition all the robots, basically, from the macro scale to the nanoscale, like even nanorobots operating inside the human body. So the relationship between robosphere and the other spheres of Earth system can be described as interdependent, since it employs matter energy to produce a form of embodied agency. So basically, the robosphere requires matter and energy to produce something, so which is the embodied agency, and we can use it in many ways to produce like goods and services. And this embodied agency is taken an expression as an interaction. And this interaction can happen in many ways and in many directions. So it can happen under the form of human-robot interaction or nature-robot interaction and robot-robot interaction. So I mean, when I say robot-robot interaction, it means robot towards interacting even with other kind of machines. And then, so the robosphere exhibit characteristic, characteristic property of complex system like feedback, hierarchy, and emergence and networking and non-linearity. And through all those properties is able to have an influence on other systems, like, for example, the technosphere or the human society and or the environments. And basically, here we have a kind of coevolution between all those systems. So here, basically, I describe why this perspective is different. And so basically, thinking in terms of robosphere can help us, for example, to first of all align this perspective with the theory of complex system, because we are using the same language. And this is very important. We can just disconnect from a anthropocentric point of view from robotics and focusing on something more global and a systemic perspective on the global ecosystems. And so we can just left behind the dualism of the representation of the interaction. So we can start to think about how all the possibilities of the robosphere and this interaction with multiple agents. And so we can consider the influence of robotics has on larger systems. And here, for example, I just described some future dynamics of the robosphere. So for example, the robosphere can have feedback loops with the robosphere itself or other complex systems. And this can lead, for example, to coevolution. It's possible to have coevolution of robosphere with other big systems, like, for example, human society. And then together, we can have a form of self-organization. So the ability of robosphere to determine new constraints and rules. And in order to better understand this, I'll give you an example. So, and I'll go really fast through the background. So this is Aibo. It's a social robot, very successful robot on the Japanese market. So basically, what happened? This is, I'm just depicting this an example of integrative ecology, which is a kind of subsystem of the robosphere. So basically, the user, so the robot Aibo was really popular, and the user just developed emotional bonds towards those robots, and as a form of artificial intelligence, artificial empathy. And then what happened? The company, which was the producer, just suspended the technical support, and in 2006. And what happened? The iPhone company just take over the market, offering Aibo repairs because the owners didn't want to dismiss the Aibos, and they needed the technical support. And then something emerged from this, and the company F1 start to organize mortuary rites for Aibos who which couldn't be repaired anymore, but they had this, but the employees of the company, they could feel the grief of the owners, which were donating their Aibos to the company, basically. So and they thought to organize those mortuary rites to pay respect for the grief. And so in this system, we have three main elements. We have Aibo robots, human user, and the company. So, and it's possible to identify a relationship of interdependence between all those elements, and a form of self-sustaining organization. Because basically, the company with all those activity could prepare Aibos and allow the users to keep going with their relationship with their robots, basically. So, and here I've just depict a scheme. So we have the Aibo robots, which is dependent from the human user to have access to the electrical grid, and even to the I mean, some specific model of Aibos, they were able to run the Aibo Life software, which was a kind of feature to develop the Aibo personality. And the Aibo was even depending from technical support from the tech company. And the human user was depending because the emotional bond from Aibo and from the Aibo's mortuary rights from which was provided by the company. And the company was depending on Aibos because Aibos was a source of spare parts for keeping going with the activity, with the repairing activity. And of course, the company was even depending on human user because the human user were providing a demand on the market. So here we have a table with more detail about the integrative ecology and a description of the manifestation in the Aibo system of the theoretical notion. But I cannot go into detail. So I'll just go straight to the conclusion. So basically, the robosphere invite us to a shift from the anthropocentric perspective towards a new ecosystemic perspective on robotics. So and robotics become an integrative component on the planetary ecology, for the planetary ecology. And so engrounded in a complex system theory, the robosphere reframe our relationship with the nature, with technology, and with the society, and fitting us in this continuum of relationship. So thank you so much, and I just pass the microphone to Luisa.
I think we can try to make one question after each talk, considering that we didn't spend all the time we gained because of the absence of Hagen with technical issues. So is there any questions from home? Please. Give you the microphone.
Thanks for your talk. I'm wondering if there's any difference between a robot and more ordinary machines or something. So like in many used car industry or used car maniacs, they sometimes lose chance to fix their old car, and because of the lack of the parts, because they're pretty old, right? So they exchange certain parts between unrunnable, totally broken old car to new, no, not new, but still okay level old car. And I think same thing is happening as the eyeball. And I'm wondering if there's something different happens after the robot becomes the robosphere instead of technology becomes a technosphere. Is there any something special in robots?
Thank you so much.
Okay, thank you for your question. Yeah, so I think it's very hard to draw a line between a machine and a robot. For example, if you think about like driverless car, I mean, should we call them car or robot with wheels? And as I was depicting, as I was describing at the very beginning of my presentation, I was talking, I was bringing as an example of cyber techno-social system, the an autonomous vehicle system. So probably in future we will have driverless car, and they will be all connected into a network, and they will drive by themselves. So I think it's very hard to distinguish between you know robots and cars, but I cannot go into detail. And but yes, robosphere, in my opinion, it's a kind of subsystem of a broader system which is called technosphere. And so technosphere in general is as Peter Raff said, it isn't able to recycle itself, and probably robosphere, as I described, is showing this kind of possibility. Maybe in future, robosphere will help us to be more efficient in recycling our technology.
And robosphere is also the relationship between humans and robots. It's not only robots. And probably also the relationship between robots and humans is very similar, but different for what he was referring to before, that what we call artificial empathy, which is a concept that we developed for the relationship between robots and humans. So with robots, specifically with social robots like AIBO, but also in general with robots, the feeling of us humans of interacting with, of being in company with someone is much stronger. And so the affective relationship or the affective form of coordination, because it's not a relationship like human-human or human-animal, it's something different. But this kind of form of coordination is very strong, as it at the basis of processes that are supporting sustainability like the one we saw in AIBO. So I think this could be a difference, a specific difference on which we could build this conceptualization. I hope I answered. Thank you very much. So, yeah. We don't have really time, there is your talk, but maybe we have the discussion later. So, okay, so we have, oh, sorry, I missed that.
Yeah.
I missed that, but start to. So now we have the second talk, Fernando Rodriguez Vergara, the self-producing automaton. And for who wanted to intervene, maybe we get back later.
Okay, honestly, I have never thought about that, and but what can I say? Probably Umberto Maturana wasn't that wrong when he was talking about the degradation of human relationship, and maybe those integrative ecologies like Hypo, yeah, was filling this kind of void left by the degradation of human relationship. I hope I have answered your question.
Thank you. Mhm. Okay. I don't have any notes. Better like. Yep. Hi everyone. I'm gonna be talking today about how can I? Okay. My name is Fernando Rodriguez. I'm gonna be talking today about this idea. For those of you who saw the keynote in the afternoon, it's quite a similar approach, let's say. Okay, so there's always been this kind of connection, or there's always been the wish to connect somehow life and computation and try to understand one in terms of the other, specifically try to understand life as regularities, right? And by computation and regularities, I mean that when we speak of computation mathematically, what we do is try to understand things that will happen in the same way automatically whenever you do them in the same context, right? So in the beginning of cognitive science, there was this idea that everything was computational. And as you know, like for a Turing machine or any other automata, you normally have this state transition table, right? So if you're here, depending on your own state, depending the input that you have, you're going to transition into a new state. And you could say that that could apply not only for cognitive systems, but for biological systems more broadly. And sorry. The problem is that, as you know, living systems don't have like a state table, right? And that was one of the main problems as in activism. put forward against this idea of that everything was computational and things, right? And enactivism from the beginning, before it was called enactivism, right, from the idea of autopoiesis, had this idea that biology and life itself was something fundamentally different than computation in terms of information processing and in terms of this, what I was saying, the state transition table, for instance. The thing is that as these ideas were developed, they took kind of, let's say, uh, an interesting direction into something that we could say that is quite similar to a computational view. So, for instance, Varela in '79 took the idea of autopoiesis, which more, let's say, conceptual, and put it into autonomy, in the notion of autonomy and organizational closure, which are mathematical descriptions of systems that have recursive dynamics, right? And then Varela with Thompson and Roche in the embodied mind, and in other work related to it, basically present the idea of an action as something that you could consider a mechanism, a cognitive mechanism, right? In which basically depending on the state of the system and depending on the state of the environment, the system is going to transition into a new state, and that is basically what we call an inaction. Then, at least formally, the idea that we are left to is this one. We can see organizational closure as something that is totally closed, in which the states are connected, and the transitions of the states only take you, for instance, if you're here, there are some, I don't know, given some state of the environment, then you're gonna transition into this one, and this one, and here, and there, you know. Basically, you have an abstract loop in which the system is always transitioning among different states of the organization, right? And you can describe this very simple with as recursive dynamics, right? In which this could be the states, arrows are the transitions, right? Which would be enactions if you go into the more inactive kind of descriptions. But the thing is that it seems to be the case that what started, this is an example from one of experiments that I did, in which you start and the thing that I just wanted to show you is that this can go much and more complex, right? So the thing that I wanted to point out is that although enactivism started with this idea that life was fundamentally something different than robots in this case, or than machines, or that whatever we can describe with computation, it doesn't seem to be the case. And insofar as you can describe the processes, because think it this way, when you have any autonomous systems or any autonomous system or any living being, and if we believe that embodiment is right, basically you don't need a state table, and you don't need a state transition table, because the interrelation of the elements of the system are basically encoding the information for the transitions, right? So what is happening is that, let's say, I see a given wavelength, that wavelength, given the the neural circuits in my brain, produce some information, and that information makes me react in some other way. So this is the only difference that I think is quite important to point out. Oh, sorry. So what I think is the main difference between what we understand as computation and what we understand as life in this specific respect is that computation is something that is only abstract, right? So in the Turing machine, for instance, you have the infinite tape, which gives you infinite memory, and you have all the time that you want, so you don't have problems. That's why Turing machines basically can do anything that is computable. But in a physical universe, right? Even if we can understand the relations of the elements of the system as encoding the transition table of the system, which is constantly regenerating, given that adaptive autopoietic systems have to self-produce, right? Whenever they self-produce, there's a lot of noise in the real world, right? So what they produce is not going to be exactly the same as it would be the case in an abstract mathematical device, right? And this is what I think is the idea, that in real life you have organizational closure also, but insofar as a physical realization, which is adaptive, is going to introduce some changes that you wouldn't normally have in the mathematical descriptions. And now, so if we consider this as cognition and computation, like let's say some link between cognition and computation, right? The interesting thing regarding the robosphere would be if we think it in a very functional way, right? Because we don't really need to. I'm trying to say in the same way that autonomy moves away from the specific instantiation of autopoiesis, we could think that the robosphere, let's say we want to, and we were discussing this with Antonio a bit before, let's say that we want to send a lot of robots to Mars to establish a colony or something like that. They don't need to be as we would normally construct them here in the Earth, right? So normally we have this idea for those of you who have played the Nier Automata game, this guy from there. We normally tend to think that if we have really evolved robots, like or at least me, they would do things like we do, right? But, and we think that if we want them to self-produce, we would need something like this, right? Like a machine for self-production. However, there could be things that are not so obvious or not so classical. I like this one, I like it quite a lot, you know. And the thing is that probably I think that definitely it's not going to be something like this. It's not going to be something like the things that we are used to it or the thing that we have in our imagery. I think that self-production or autopoiesis in robotic system first is not going to be same as us in the sense that it's not going to be the self-production of a robot, but it's going to be probably the self-productions of whole systems. Systems, and I mean system in the sense of many robots creating the factories that create the robots and something like that, rather than the reconstruction or the recreation of the individual. Okay, so these are the conclusions. Thank you very much.
so we can't hear you.
Why?
No.
And now you can hear me. So, yes, fantastic. Now is the moment of Nomura-san, Nomura-sensei. Can you hear me?
Yes.
Yes.
Yes. Thank you. Can you hear me?
Share the screen.
Okay.
We
So
hear.
from Zoom is okay?
Yes.
Yep. Please wait for a while. 運動表示で、これで、シェアは、ルイザさん。
Yes. We see it very well.
Yep. Okay.
Fantastic.
Great. So, may I start? あれ、大丈夫?
You can start. Yes, yes.
Okay, thank you very much. So thank you for giving me a great opportunity to introduce our recent works. So I'm Shin Nomura from Tohoku University. Maybe you are in Kyoto, and so I'm very far from there, and about 100 kilometers north east. Yeah. And so I'm working with molecular robotics vibrations. So we are creating some kind of good designed molecules, and so creating the systems with the molecular by molecular interactions. And I'm sure so such kind of constructive manner can expand the possibility of every materials. So that can have in the future, so they have our own consciousness, so some kind of the mind, so etc. And so we can become a good friendships. I hope that. Yeah. And today's title is about so environmental responsive multi-compartmental systems made by molecules. Yeah. So we have worked with artificial cells, left-sided one. So I hope you can see my pointers. You can see? Okay. Now?
Yes.
Yeah, okay. And so we also published one paper called the world first molecular robot with changing the motions with a molecular clutch. That is completely different from the real cells usage one. That is originally designed by non-genetic DNA. Okay. So from the molecular robot or artificial cells, we think the more powerful or more, how to say, useful or more to exchange the information can be able to talk. So from the real life and artificial life. So it needs auto productions. Last presenter says also that the production it's made on the production program. And so of course molecules have own programs, and so we need the kill switch from the outside, external control for the safeties. Because of that, I'm a part of graduate school of engineering. Yeah. But so if such kind of molecular system is gradually established, developed one by one. So yeah, so self-replicating machines in safe will be realized. That is our one feasible stories. Yeah. And this slide shows our examples of molecular robot with artificial cell type. So they are not including the gene expression systems or central dogma of our real cells. But so it can switching the motions, and it can input the molecular signals with the DNA pores, and yeah, it can get some non-genetic molecular signals as a building block, so DNA molecules or RNA molecule from the outside to inside. Yeah. So this artificial cellular membrane is made by very thin, oily membrane, and it cannot penetrate, it cannot pass the every hydrophilic molecules in the water system. So we need some pores or some kind of transducers. And if the transducers can pass the signal from outside to inside, so please imagine you will, when you create some electrical robot or electrical systems. So if your signal is very weak, we need to amplify the signals. Yeah. So molecule also the same problem. So we can put we can design the one very effective molecular amplification signals. So with Jamstack, so with a teammate of the Kuruma-san's, Yutetsu. So I miss him today, but yeah, his colleague Komiya-san help us to create the DNA amplification circuit within half an hour. So 10,000 times, over the 10,000 times, increasing the DNA signals. Yeah. And so the leftmost upper side, I'd like to introduce the new molecular controllers, molecular programming. Just 2 lines of the programs. One is, okay, green guy and so red guy gathering. And the second line is, okay, you're well packed with as a yellow condensed swimmer, then you can purge. Yeah, just 2 lines. But so combining the molecular DNA molecular controller with molecular motor system, that is a very tough problem. And so we spent 9 years, too much. Yeah, but so it has succeeded, and so Science Advances can accept our papers. Yeah. Okay, and but so the molecule has a many type of modality. So single molecular type, and so a complex compartment, and so micelles, and so maybe so you remember the yesterday's Nobel Prize of chemistry. So our Japanese owner of the Professor Kitagawa got the Nobel Prize with a macromolecular complex with multiple pouring systems. That is also can be used. But so the micelles, so phase separated structures, so liquid condensed manner. Yeah, and so water in oil droplets. That is very highly barriered from the by oil, and so riposome, which is a kind of the cell models, and the gel. So now we are going to see the new bodies of a multicellular type. So because of the single cell type molecular robot or artificial cell is floating in the waters or the waterish medium, and that is very thin. And so how to exchange the information is always problem or issues. So if the multicellular system is existence and so made by in easy, so it is very useful, I think. So this is examples. So we call this as millimeter scales. So artificial multicellular systems automatically made from the hydrophobic sponges automatically. But so our ex-postdoc, Richardson from UK, succeeded to create the more huge bodies. We call this the centimeter class. Yeah, dreadnought class or centimeter class. Yeah. So we do not need the microscope, and so we can touch them with our real hand, and so we can see them bare eyes. So yeah, without without microscope is okay, and so we can put the very small magnetic nanoparticles with just a pipetting macroscopic, and so if so, they can react from the external magnetic field. Yeah, some people or many people call it is a cheat. Okay, that is yeah, that is a normal way. But anyway, this is how to create the multicellular systems. You just mixing the internal water mediums with a repeat ink and put it onto the water. So it automatically creates centimeter scales existence. I think this is not so bad. And so just a pipetting technique, so you can put completely mixed one and layer by layer structures like skin, real skin. Yeah, so it is very easy, and so now we can enjoy creating these kind of artificial cell systems with junior high school people and normal citizens. Yeah, non-academic peoples can enjoy to create the artificial cells. And but so enthusiastic student, so we love such kind of student because of so we are in the department of robotics. So he tried to create the robot, automatically creating the molecular robot. Yeah. So the robot arm puts the sponges onto the water-ish medium and liquid handling systems uses the solutions one by one. And so then, the well plate is set it onto the automatic microscope. And so they check the every images, and so they check the conditions. This condition is okay, or this condition is not so good, and so they can they show us the data automatically, and then so the next experiment will be loaded onto the robot, so it can make the experiments easily. And so now we are trying to use AI and data lake to create more good, also better and better molecular robot will be designed automatically. And so, of course, the gene expression system can be loaded with these artificial systems. And the productivity is not so high, but 2 times compared to humans. And so how to use it is, this is one example. So centimeter scaled multicellular bodies incorporated in the hydrophilic gel, like agarose. And so we can keep it in the room temperature without any special conditions. So in my pocket, it can keep safe at least 2 months or so. Yeah. And so it can respond with external salty conditions. If the NaCl or some kind of the magnesium also okay. So like a sweat, the model of the sweat, it can react to gradually puncturing the multicellular systems. And the contents is gradually released, response to the external sweat. So it should be contribute to mobile health or some kind of the human happiness. I hope that. So because of so this Inaba-kun, his ex master course student, he was actually rugby guys. So and so he wanted to get some exchanger of his not so good smell of the sweat to the good smell. So partly realized, and yeah, this is a graph of reactive from the external salty conditions. Yeah, when the salt concentration is increased, the outside water issue media's concentration is increased, and the surface tension of the multicellular system started to decrease. So this is came from the shift of critical micelle concentrations, the chemical maniac word, but so it can realize the gradual puncture of the multicellular systems. And so when you put the two type of model drugs, one is red and the other one is blue, and so put them into this rocket shape tube, and so the hip of the rocket is freely exchange the waters. If so, at first the red drug, model drug, automatically released at first. Then after that, the blue drug released one by one. Yeah. So what is the key point? This is it shows not so sophisticated mechanisms, but just a shape of a rocket or shape of the gel can realize the output pattern, output time course of drugs. We think this is not so bad. Yeah. Yeah, now the system, oh, I'm sorry, so time passed. But these three type of the conditions also made in easy, and we are now trying to exchange the information molecules so nearby the compartment. So what are the sensors? So of course the oily membranes do not allow to pass the ions or small molecules or the DNA or RNA or proteins, highly complicated molecules. But so we need some pores pass through the oily membrane. So these orange lines is the oily membrane, and just 5 nanometers. But so their barrier effect is very high, and so we need to make a pore to passing even the small molecules. So we realized this kind of at that time, so world hugest pores on the artificial pores on the membrane. But so now they started to expand and expanded. But yeah, even in the 10 nanometer by 10 nanometers pore, that was a very leaky. And so, of course, so you can imagine that just a proton or so potassium or the magnesium also can easily pass through the pores. So we made some lid onto the pores, but so the lid is not perfect, and inside and outside world is completely same becomes completely same conditions. Yeah, that is not a living state. This is not a real cells, but so if the membrane potential goes to the zero, so the robot also cannot use its information from the outside. So the new step is chopstick type molecular sensors from outside to inside. But so yeah, some type of molecular sensors were published, but so that is an on-off type, and they do not they cannot use direct information from outside to inside of a DNA molecule. So our new one is called Chabashira. Chabashira is so Chinese or Japanese sign of the happiness or good or lucky. Yeah. When you are lucky, so tea leaf stem can stand. Yeah. Become stand. Okay. So the mechanism is like that. So single-stranded DNA, of course, this is not genetic information, but so a part of the DNA, single-strand DNA, is modified with a cholesterol, oily cholesterol. Yeah, so it can attach to the outer membranes. Yeah, when we call this as a packet, the molecular packet. When the single-stranded DNA hybridize with these driver molecules, it start to create double helix and so dense packed hydrophobic molecules, and it's desirably stand and onto the membrane. Yeah, and so the end of the packet, single-stranded DNA can pass through the membranes. So that is our original design, and so we succeeded here. So our molecular beacons, when the desired molecular information came, the beacon started to open and shows green or red. Yeah. If you put the beacon molecular packet from outside, so opens the green signals, the membrane goes to green. And so the red packet shows red. And so both red and green, it's turned orange or yellow. And we, this is a little bit so maniac, and so we calculated the efficiency, and it is not so good, not so bad, and we finally succeeded to create a drive the internal molecular circuit from the external molecular informations input from the outside. Yeah. So so I will skip the details, but this DNA circuit realize the last time I show you the increasing the DNA informations automatically. So amplifications. Yeah. So this figure shows about 25%, 29% of the efficiency. But so now we succeeded to realize 75% of the base course, or so molecular robot can recognize the external signal. Okay. Yeah. So this is 75% driver plus packet. And so we also succeeded a kind of a pump from outside to inside, and so inside to outside. So we can peel it up, or a kind of the tug of war. So molecules can be picked up from the inside or so outside, from outside to inside. But so, yeah. So now we can find the way to pass through the molecular information from outside to inside to outside. And of course, the neighboring compartment can be talk with molecules. So DNA computing system is now freely or so design exchange their informations from with the outside world or the neighboring world. Yeah. So now we are trying to create the multicellular bodies with the Chebyshev systems. And so we also have a Marangoni motors that it is very quick, 30 millimeter per sec, swimming on the water medium. And now we are trying to think about so not only the cell, so elder people or senpai, we call it, but so the insect size molecular robot will be realized, and so we can learn a lot from the natural systems. But so we can, not just learn, but creating the original ones. So this is not a method acquired by organisms through evolutionary history. This is robotics. So applications are on-site genetic diagnosis, so crypto something, and so toxicology testing or some kind of that. So now we are stepping one by one with the molecular design and so molecular. Okay. Thank you.
This is absolutely interesting.
Thank you.
Thank you very much for your talk. Any question? Maybe we have the time for one question. I don't see questions. So maybe I can make a question.
Thank you.
When you write that this is not evolution, this is robotics, you also mean that this kind of structure doesn't have a spontaneous behavior, for example, the multi-body structure. Does that any spontaneous collective behavior, or is simply determined by,
So that is a very interesting point. So now our students starting to create the automatic reconfigure systems over this multicellular component. Because of that, so as you know, when you eating the ramen, the many kind of the oil droplet is onto the not just the ramen, but soup. Many soups has a oil droplet, and they can reconfigure the here and there. So this multicellular system also can be exchange the conditions, and so if the Chebyshev or some kind of molecular exchanging systems realize the neighboring talking, so reconfigure and so changing the information under some memory storage. And so I didn't say today, but so we realize we already realize Pavlovian reflections of molecular systems. And so, very short range very small memories, but so yeah, can be stored in the compartment. And so yeah, running and exchanging the memories and yeah, some kind of mm, なんだ、actuations for in the real world can be creating some kind of yeah, automatic self-organizing motions or something. Yeah. Is that
Thank you so much.
thank you?
There is another question. I read the question because I imagine.
Yeah.
Pasquale, you want
Interesting works. Thank you, Pascal-san. Ciao. Thank you for sharing the result as a particular rights aggregate with that to do this instead of possible main
So very interesting work. Thank you for sharing results with us. I particularly like the aggregate results. Do you think it is possible, thanks to internal reactions, to generate different regions in the large aggregates differences? This can impose a system-level constraint to individual compartments.
Yes, thanks. That is a very nice point. And そうね。Yeah. So the last time, so Lisa-san also asked me that, yeah, I replied that the main the membrane's main component is the oil. And so, yeah, you know very well about the oil cannot shield the electricity. So, yeah, so if the local, the electric potentials changes, the effect directly affect to the neighboring compartment. That can the length of the between the two compartments is nothing, I think. Yeah. So it's immediately exchange the information, the electric information. So I tried to use backside down or opposite side vesicles in the waterish membranes inside and outside the oil. And so the membrane part is the water. So one of my students realized to that. But so, yeah, such kind of the water membrane in oil, the reverse vesicles is automatically attached to each other because of that is electrostatic powers can pass the oil phase freely. Yeah, but that is a very nice point. Yeah, that kind of the information propagations should be think about that. Yeah, please discuss later. Thank you.
So thank you again. Thank you very much.
Thank you. Yeah.
This is really, as Eric said, impressive work. Now we have a break. We are already delayed for the coffee break, but we still have 20 minutes of break. We'll be back at 4. Thank you very much, Nomura-san.
Thank you very much. So have a nice
coffee
break. Thank you. See you.
So coffee break for another 20 minutes. I think we can start. So the second part of the workshop. The next speaker is Francesco Bianchini. Ciao, Francesco.
Hi everyone. Hi, Luisa.
So you think you're able to share the screen?
Yes. Oh no. Okay. I have to go out and reopen to share the screen. Okay.
Yes, you're appearing.
Okay, fine. I hope that now will work. Fine. Now, okay, this is my presentation. So, can I go or?
Yes.
Okay. So, from your answer, I also understand that you can hear me. So, thank you very much for let me be in this 10 edition of the workshop. I will speak about a theme that is connected to one that I dealt with more than 10 years ago, and that was related to the synthetic biology, my first interest in synthetic biology, that is due to Luisa Damiano. So I will speak about superorganisms, and I'll try to connect this notion to the one of robosphere. So the overview of my presentation, okay, is that I want to show that, I want to state that superorganism and cognition are in a bidirectional relationship. The first one is from cognition to superorganisms. That is the one that I dealt with 10 years ago, and the second one is the from superorganisms to cognition, as is today core of the presentation. I want to show that superorganisms are as multi-level and articulated systems could be inspired for swarm robotics in a different way, respected the way in which the superorganisms are a paradigmatic example of swarm behavior, swarm intelligence, through the notion of robosphere. So let's try. Yeah, the idea of comparing intelligence or reasoning to superorganisms is not so new and has a twofold aim. The one is to determine whether a form of cognition could be identified within some complex biological systems that are with the particular properties. They are one system formed by many individuals that are not connected, physically connected, not always physically connected. And the second one is to explore whether these systems might provide insight or explanatory models of cognition or human cognition. From cognition to superorganism was the first direction. I was inspired by I used the biocomputational approach by Holdover and Wilson in describing the social insects and superorganisms, especially ant colonies. They in 2009, their book is in maybe 20 years ago was written. It was an analysis of ant colonies and superorganisms using concepts from information science and computational theories, especially when they describe the agents, the ants in the ant colony, as basic units of the systems that execute simple algorithms. So the ant behavior is described as an algorithmic process, and like in an algorithm, this leads to decision points, different decision points. These decision points are also some different pathways of groups or castes that are specialized groups of ants. So in these systems, we can find some complex structure that is able to perform complex tasks at a multi-level as a multi-level system, because there are the individuals, the ants, we have the groups, and we have the system as a whole. This complex structure is able to communicate through stigmergy, to explore the environment, recognize what matters for the colony, and in a certain sense is able to preserve knowledge in the shape of distributed information between individuals and especially group specialization. This is thanks to the loss of some features of the of the ants. So ants are more specialized, not more complex. They lose some tasks or ability to do some tasks, and they can specialize in some specific task of a specific group. So an ant colony is different groups of the same individuals that are with different properties due to the colony to perform specific tasks. So it's a very articulated system. So this is an example of the the process of the individual. So it's could be a series, could be some different series of tasks in parallel, but also there are processes that are in series and in parallel. They can exchange during the evolution of the colony. So in this these systems is able to do something that we know as cognition with a sort of specialization of a higher part of the systems that are the groups, even though the individuals keep a sort of individuality, a degree of individuality, and this structure in which the individuality is not fully lost allow the superorganism to be superior to the organism in the sense of flexibility and robustness. And the intelligence of the systems, or the way in which we can say that they have cognition, is a sort of ability to understand the information in environment through a sort of organizational net structures that is provided by the intermediate level of the system, so the groups. And yet, the way in which you identify a superorganism is very different from the way in which you identify an organism, because we have to give up the criterion of physical cohesion, especially in ant colonies, also in bee colonies or other kind of superorganism, and there is no physical cohesion. And so, how can we identify the same task, the same abilities, the same capability as, for example, in an organism, high order organism like a human being? In Aldober Wilson, we can find this table that connect the part of human being, for example, mammal, with part of the superorganism. So we have the cells that correspond to the colony members, organs that are cases, and also some functional part, nervous system, communication and interaction among colony members through stigmergy, the skin or the skeleton are the nest. I can say that the criterion that we can use in this case is a sort of criterion based on parallelism or analogy. Using this criterion, we see that there has been in more recent years some attempts to identify cognition or features of cognition in superorganisms in a computational view. For example, these studies on psychophysical laws and superorganism, or this other on the psychology of superorganisms, that is on collective decision making. So the use of the vocabulary of cognition or cognitive science or psychology to analyze the behavior of superorganism is not so widespread, but it is something that it was used, for example, in entomology or some part of entomology. But how can, if this is the part that is related to the import cognition into superorganism, how can we say that, how can we import superorganism into cognition? So the other direction. This is an old idea because for the first time, as far as I know, it is in Gödel Scherbach by Hofstetter in a dialogue that is Prelude and Fugue in which he described an ant colony as a sort of cognitive systems like in the following decades superorganism has been meant but this is direction I think that is less explored in a computational way in especially in artificial life because superorganisms are paradigmatic example of swarm intelligence since its beginning at the end of the 80s, on the first 90s of the last century, because of some feature like the emergent activity, the interaction of several individuals that are interconnected. Yet, I think that in literature that just a partial inspiration by superorganisms has been used in the swarm-based framework of robotics. That is the computational counterpart that I am considering here. So, for example, communication mechanism, collective behavior, self-organization, and so forth and so on. Usually, I saw that in swarm robotics, the focus are on individuals and the collective behavior on individuals that have usually the same role. So they hunt, so we have studies on ant robots or on ants as molecules that process information, energy, and matter. But superorganisms are more complex than this. So, for example, here we have the Myxobacteria or the Portuguese man of war. They are multi-level and articulated system with maybe the same DNA, the same genetics, but different behavior at different levels. For example, Myxobacteria are able to produce secondary metabolites in their behavior coupled with the environment. I saw in literature that sometimes the different robotic swarms are studied to see the interaction between them, but there is not a consideration as an articulated system as a whole. So, how can implement in swarm robotics these articulated systems that are many and one? They are many and one as individuals, that are many as roles, and one individual as a functional roles. They are united and separated because I think that this kind of systems and colony, big colony, Portuguese man of war, Myxobacteria are different. They are not the same, but they share this being one and many in role parts, and also they share the flexibility in being in the world, the flexibility that is the lack in physical cohesion. So I think that, and that this is my claim of today, that the robosphere notion could be useful, maybe also through the attempt to define and use sustainability as a core notion to better characterize the swarm robotics that may be derived from superorganisms, an advancement in swarm robotics that it could be more connected with the features of superorganisms that are not just a collective emergent behavior of many individuals, but are more multi-level systems. So, if we consider the classical feature of self-organized systems, for example, the autonomy, the closure notion by Varela about the relations among components that produce the individuality, the organization, the coupling with the system environment. We see that all these kind of features are also features of superorganism, even though we have not the physical cohesion in some cases, because the important part is the network among relations, the network relation among components that could be present also in superorganisms. So the the point is that if you want a superorganism-inspired swarm robotics, we have to use to exploit this the fact that they are multi-level articulated systems, and try to build these systems starting from the parallel interaction with human being cognition. This is, for example, if we consider not just the robotic part or the human part, but in an interaction like the one that is defined in robosphere, we can say that the artificial system mirrors fluidly the human functional organization, and the artificial system interacts cognitively with human cognitive system, and also in the other way. So the human cognitive system could interact with an artificial system like this cognitively. It has the interaction is understandable at cognitively at a cognitive level. So if we consider a whole framework as a self-sustaining, a whole framework that is inspired, the robotic part is inspired by some multi-level system like in superorganism, and the human part is able to interact, because at the higher level we can have the parallelism of cognitive abilities. From this point of view, I think that we could have some insight on cognition and some useful application in swarm robotics. So the robosphere could be the next framework for developing a swarm robotics that is more aligned with some natural features that we found in this particular natural entities like superorganisms. So thank you for your attention.
Thank you very much for this very interesting talk. Any questions? Also from the online audience? Please. One question is arriving.
Hi, thank you for the nice talk. I was wondering, your vision of this film, if humans and robots have to kind of form this superorganism, would robots need some form of agency? I mean, some form of independence? Because if they are totally dependent on our decisions, is it really kind of an amalgamation like a superorganism?
I was not able to understand the question. Can someone repeat it? Can anyone repeat it, please?
Asking, you hear me?
Yes. Now better.
It's really a problem. Which Francesco I had to lately in a conference, so it's not aging, or it's a common problem of aging. Anyhow, he was asking, considering that robots are completely dependent on us, they can constitute a superorganism or not, or they would need an agency or more independence from us.
Yeah. Okay, thank you. I understand. Now, I think that the interesting point is that superorganism has a sort of agency or independent behavior, as we have an independent behavior, but the connection between them and between this kind of independency can produce a sort of mutual dependency that can produce emergently more complex behavior, considering the fact that we can interact with a more complex system like the superorganism that has to maintain the individuality and the agency in a strict way, like in the biological counterpart. So I think that this kind of individuality is the individuality of the superorganism as good and strong skills that we will be able to use by interaction for further emergent collective behavior in a sort of robosphere framework, but preserving the individuality, because it's a plus of the superorganism that is not the total independence. In interaction, the two independencies becomes interdependencies.
1 second.
Hi. But yeah, I think I understand. I think I understand. But can you hear me?
No, I cannot hear anyone.
We don't understand what's going on. Can you hear me?
Yes, yes, Luisa.
1 second, I'm getting the question for you. 1 sec.
Okay.
So basically, Fernando is refocusing on the fact that robots are depending on us. They do not have an independence like us as complex systems. So they're
Okay.
like tools.
Yeah, okay. I understand. Yes, it is true. It is true. Maybe they are dependent on us, but they have also some autonomous behavior that could be enhanced by the fact that they operate collectively. So I think that there will be maybe an asymmetry for a long time in this kind of view, or maybe a wanted asymmetry. But I think that the interaction could produce also in this case some emergent novel behavior. There is also a question by Pasquale in chat. Pasquale, the human robot superorganism scenario would require that robots are aware of our existence. Big question. Is this required, or perhaps simple relations would suffice? I think that we can be in an applied view and consider that the simple relation would suffice to create a robosphere. The fact that robots are aware of our existence is a different question. Maybe it could be a question that this kind of framework could produce some insight, but it's a philosophical question, so it's a question also for me. But maybe if we have a shared idea of what is existent, or if we can establish a framework in which we can share the same notion of existence, it could be in this kind of framework, but maybe it's a consequence, not a requirement.
Okay, thank you very much. Thank you again for your talk too. And so now is the moment of the next talk. Is Rebecca Mannocci modeling the robosphere through biorobotic art, a bioaesthetic inquiry. 1 second that we switch device. Puoi usare questo? Tanto sono. Sì, sì. Perfect, we see you. You can start. Yes.
Thank you very much. The talk today will focus on the concept. What? Oh, are you hear me from online?
Yes, yes, very clearly.
Okay. The talk today will focus on the concept of the robosphere and how we might rethink its meaning and implication through the lens of bioaesthetic, and more specifically through biorobotic art. And my three objectives are to conceptualize the robosphere as a milieu of individuation and emergence, drawing on their interpretation of the concept of robosphere by Antonio Fleres, and the philosophy of Gilbert Simondon, to introduce the idea of a bioaesthetics epistemology as a way of understanding and engaging with hybrid techno-organic systems, and to explore how bioart and biorobotic art, in particular with the work of Ken Rinaldo, can serve as modeling practices for imagining artificial life and the future of human-robot coevolution. In recent years, robotic systems have increasingly become part of both natural and social environments. This growing entanglement has given rise to the robosphere, a hybrid dynamic space where technological, biological, and cultural processes intersect. The robosphere is not a mere technical domain, it is a field of relations where machines, humans, and living systems coexist and co-evolve. To conceive of the robosphere as a milieu means rejecting the idea of technology as an isolated tool and adopting a critical view based on the theory of complex systems, as Flerer said. Instead, the robosphere films is embedded within broader processes of individuation and relationality. According to Simondon, individuation is not a static essence, but a process of becoming, where entities emerge in relation to each other and to their environment. From this perspective, robots are not inert machines, but participants in processes of co-individuation, interacting with humans and other living systems in evolving ecologies. This relational perspective allows us to consider the robosphere not as a linear extension of human design, but as a complex emergent ecology. In this view, the robosphere becomes an in-between space, not purely artificial, not purely natural, but a zone of encounter where boundaries blur and new mode of subjectivity and agency can take form. And this also means that understanding and shaping the robosphere requires epistemologies capable of grasping nonlinearity, relationality, and interdependence. If the robosphere is to be understood as a social tech hybrid milieu of co-individuation and emergence, then tools for apprehending must go beyond the traditional analytic frameworks. And this section argues for the development of a bioaesthetic epistemology, an approach that foregrounds relationality, embodiment, and artistic experimentation as essential to understanding the complex techno-organic systems. A biostatic epistemology resists reductive separation between subject and object, aligning with modes of knowing that are immersive, participatory, and responsive to the morphogenetic processes of life itself. Such an epistemology does not treat the robosphere as a closed or objectical domain, but as an open dynamic field where knowledge is always partial, situated, and co-produced by human and non-human agents. This perspective finds resonance in the practice of bioart, where living matter becomes not just material, but collaborator. By working with cells, genes, microorganisms, and robotic components, artists create environments in which the boundaries between the biological and the technological are intentionally unsettled. These aesthetics experiments for insights into the affective, ethical, and relational dimensions of robotic life, central to how robotic systems are experienced, imagined, and co-evolved. In this framework, aesthetic is not a matter of expansion, but a mode of connection, a way of thinking through making grounded in active principles, capable of engaging with the complexities of the robosphere. By cultivating a bioaesthetic epistemology, it is possible to reimagine robotics not as an external intervention into life, but as a part of life's own unfolding. This shift opens the way for more nuanced, ethical, engaged forms of coevolution, ones that prioritize care, reciprocity, and creative experimentation over domination and control. Unlike representational art, bioart practices operate on the material level of life itself, genetically modifying organisms, integrating biological and robotic components, and creating semi-living systems that challenge our ontology of the artificial and the natural. In doing so, they provide powerful models, not only metaphorical, but also epistemic, for understanding coevolution, adaptation, and the relationality in hybrid ecologies. As a modeling practice, bioart does not aim to simulate the robosphere, but to instantiate its logics, emergence, interdependence, contingency, and co-individuation. These are works enact rather than illustrate the principles that govern complex living technological systems. They expose viewers to material processes of transformation, interaction, and negotiation between life forms and machines, thus allowing the robosphere to be experienced as dynamic, affective, and often unpredictable environment. For this reason, bioart and biorobotic art installation can be considered ontological laboratories, where speculative scenarios unfold and where conventional distinction between animate and inanimate, natural and synthetic art and science are dissolved. They invite the audience into an interactive relation with hybrid agents, that be modeling not only of knowing and being interactive relation with the hybrid being with technology, but also in form of subjectivity, in which emerge the concept of per-human space, a zone of negotiation of shared meaning. These works are not neutral experiments, they are ethical aesthetics invention that confront us with the ethical implication of manipulating life and merging it with artificial systems. In doing so, they open space for reflection on the trajectories of robotics and biotechnology, beyond narratives of domination, optimization, or utility. They ask, what kind of future are we shaping? What personal care, responsibility, or reciprocity must accompany the creation of semi-living agents? Crucially, bioart operates through relational aesthetics. It emphasizes the condition of encounter, cohabitation, and the affective resonance between human and non-human actors. And these practices thus become valuable models for understanding the robosphere not simply as an abstract system, but as a layered ecology, an entangled network of interactions in which meaning, agency, and responsibility are continuously negotiated. In this context, in my opinion, the work of Carinaldo is particularly significant. And one of the most emblematic work in this regard is Augmented Fish Reality, is a robotic installation in which Siamese fighting fish interact with mobile robotic platforms. Each fish resides in a bowl mounted on a robotic base, which moves in response to the fish's swimming direction, allowing the fish to navigate the space. And the result is a form of cross-species interface, a biocybernetic environment where organic behavior modulates robotic movement and vice versa. Rather than being a mere spectacle, the work invites viewers into a speculative ecosystem where agency is distributed across species and substrates. Have a very little look of the art. I'm sorry, but in this part of video, robotics installation isn't moving, but you can imagine the movement. I didn't find a video of the robotic movement. Similarly, his installation onto Poiesis features a network of robotic arms that responds to the presence and movement of viewers, as well as to each other. According to Rinaldo, these robotic entities exhibit emergent behavior. They appear to communicate, adapt, and develop unique personalities over time. Drawing inspiration from theories of autopoietic systems, the installation exemplifies a self-organizing ecology that unfolds through interaction, not only among machines, but between machines and human observers. The relational space of the artwork becomes a hybrid milieu in which the boundaries of self, other, and system blur. Have again a little look. According to Rinaldo, his work models the robosphere in at least three key ways: emergence, relationality, and affective engagement. Emergence, because his installations are not pre-programmed to follow linear scripts, but evolve through feedback and contingency, generating behaviors that cannot be entirely predicted. Relationality, because agency is not located in a single entity, but is co-produced through interactions between multiple actors, human, machine, and biological. Affective engagement, because viewers are not passive spectators, but participants in a responsive system that will become implicated in its unfolding logic. In these aspects, the robosphere is not a distant concept, but a tangible relational field, an ecology of becoming where ethics, aesthetics, and epistemology intersect. By creating spaces in which robotic systems live, adapt, and relate, Rinaldo offers an embodied vision of how we might do well with machines as co-agents in shared environments. This insight generated by robotic art, particularly as modeled in the work of Rinaldo, hold significant implication for the field of artificial life. Traditionally, artificial life research has focused on simulating the behaviors and properties of living systems through computational, robotic, and chemical means, encompassing hardware, software, and hardware models. However, the aesthetic and epistemological practices examined here suggest the need for a methodological reorientation, one that moves from life as a code to life as relation, and from modeling function to prototyping relational futures. This shift strong resonance in the emerging paradigm of futuring social robotics, which aims at design and presenting robotic agents to explore possible human-robot social worlds. To conclude, we can say that the robosphere can be understood as a living milieu of individuation and emergence that calls for a bioaesthetic epistemology, and where bioart and biorobotic art can serve as modeling practices for this rethinking. By moving from life as a code to life as a relation, we are invited to imagine new forms of coexistence and coevolution with artificial agents. Thank you.
Thank you. Thank you. Any questions? Fernando? Maybe it's better to stay in this area.
Hi. I really love the talk. I think it's super interesting. I actually think that if this would be like a thing, like let's say a bio-robotic, bio-robot bank, I don't know, it would be really useful for future generations of engineers and like scientists, because it would make you think very differently. My question is, I don't know if you saw the talk from Takashi Kegami. No, basically he connected an LLM to an android, right, a robot, right? And if you prompt in the to the LLM, like act as if you were happy, or even something like people is laughing, the android kind of expressed the emotions of like without any training in acting or anything. It's like the emotions were encoded in the latent space, right? In the latent space of the LLM, right? Do you think that the problem, or not the problem, the thing is that with humans, it seems quite clear, let's say, to some extent at least, the transition between emotions and words, right? Do you think with if you were to do the same with, let's say, plants mixed with machines, right, and you could somehow get the data from them, do you think there would be some way of transferring that to some other, like to some latent space that you could use for something?
I think it could be a chance to make a kind of experimentation. No, we can try to observe, and after that utilize the result, the empirical result, to construct something. I don't know if I answered to your question.
The difference between fact and science kind of discriminates.
Yes, in fact, the definition of bioart is like an umbrella. And under this umbrella, we can find a lot of different kind of art, like also transgenic art, or each one connected to the science. Thank you.
Thank you very much. I don't know if there are other questions from home for the moment. I have the impression that se puoi lasciare il tuo. There are not other questions, so thank you again.
There was a question in the chat, I think.
Pasquale, I lost it. Do you see it? From here. After some of your video, it is impossible not to think to Gordon Pask exhibition, the colloquy of mobiles, 1968, but I see that the robosphere would be even more inclusive. What's your opinion?
Yes, I agree. But as I said before, I think that is only a little piece of the puzzle, no? Because in my opinion, these artworks are just to try to set in scene something that it's very bigger. And so this is my perspective.
Thank you very much again. Thank you. And so now it's the moment of the next and last keynote from Gentiane Venture.
Thank you very much.
Hi, Gentiane.
Hi. So I'm going to share my screen if that's okay with you.
So the talk is about reflections on our experiences with robots in the wild.
Yeah. So I guess you can see my screen, right?
Not yet, but probably we have to interrupt this. Now, yes.
Okay, good.
Fantastic.
Okay, fantastic. Thank you very much for inviting me to this very interesting workshop. I am having a great time listening to the other presentations. So I hope you're not too tired, and I'm going to talk, as the title suggests, about some reflections on our experiences with robots in the wild. So I'm going to start right to deep dive directly with some of our experience in the wild so that you can understand a little bit what we've been doing and why we've been doing this and what was the messages and the like very precious information that we got from those experiments. So we've been conducting a lot of different types of experiments where we bring our robots directly into spaces where humans are, and not necessarily where actually they are expected. And so, for instance, well, we bring it to classrooms quite a bit, so there's a lot of kids interaction. We also bring it to the stage, and I'm just trying to remove that thing. Yeah, okay. So we bring it also to the theater with robot on the stage, but there's also places where we like big exhibitions where people are free to interact with the robot here. And also we had experiments where we had robots in restaurants, for instance, way before they were common. This video dates back probably more than 10 years ago, actually. So a lot of this work actually is fairly old. All of these videos with the children are actually pre-COVID as well. And that also is one of the small robots that we created. And I think it relates a lot to the previous presentation, how it is easy for us to kind of like infer and like think that robots have a very specific meaning and that they have their own agency. Even here in this case, the robot is working on the random behavior. When we're discussing and the robot moves, my colleagues here are thinking that the robot responds to what they were saying and is not happy with what she said, which is absolutely not the case. So it's really interesting to see that all of these different types of robots in the wild, where we are really able to let people discover and experience robots leads to a number of learnings. So before I go to the learnings, I wanted to tell you how this is possible from the robotics point of view. How can we manage to put all of these robots in the wild while we're doing experiments? Well, the first reason why I was able to do all of these experiments is because, of course, I have a fantastic team. I'm not going to thank them at the end of the presentation. I really wanted to thank them from the get-go. Without them, that would be impossible. The other reason why we were able to do that is because we developed along the years a framework that enable easy robot programming for people that are not necessarily robot engineers and programmers, which then helped us to respond to the needs of a number of places where we develop robots, and in particular the school and in educational settings. And then we needed a lot of creativity, ingenuity, and patience to be able to do that, and also some fearlessness. One thing that we discovered when we were doing these like experimentations is that you have to be fearless about what happens to your robot. Because if you want to have a genuine experience with robots in the wild, you have to not tell people, don't do this, don't do that, this could be dangerous, you could break the robot. We never tell the kids, for instance, like, don't pull out the fingers, don't put your fingers in the robot's eyes or whatever. We just let them be, and everything kind of go very much well. So what we have learned is quite like a number of different pieces. And the first thing is that we need to think about a meaningful experience. And that's where the creativity, the design, and is really important. Because if you think about robots in general, the image that we have about robots is that they're completely disconnected from any users. You have robots in factories, robots in warehouses, even robot in the home that is just a vacuum cleaner. The user doesn't really connect with it. On the other hand, in the research field, we have robots that are completely disconnected from any use. We have robots that are just here to be, representing oneself or be around, but they just don't do anything except they're chatbots basically. Or Asimo that was discontinued at some point. It was there just as a display for some promotion, but never really achieved anything specific. So thinking about how much important it is to create a meaningful experience is something that you have to think about. But even though you create something that seems to be meaningful for you, might not be meaningful for everybody. And once we were conducting experiments in the cafeteria at the university, we realized that some people just don't care about the robots, and I think it's fine. So we conducted an experiment where we put our robot here in the cafeteria, and it's very hard to see from that picture, but basically here is a big corridor, and on the left side of the corridor, we have our kind of like a convenience store at the university from people going from the cafeteria to the convenience store. And then on the right side, right here, we have the stairs and an elevator. And I'm going to show you a number of pictures of images of what happened when we placed that robot. So the video images that you're going to see are the video images that were captured by the camera that is posted as almost an ego camera from the robot. So basically, like the camera sees from the robot's position what the robot is seeing. So when you're a very positivist engineer, you are thinking that everybody's go and come and look at the robots and be interested and come and potentially take a picture of the robot, or just gather around, get stuck to it, and so on and so forth. But what we saw is that also some people just don't care. They just pass and they go, and they didn't even look at the robot. They didn't even acknowledge that it was here. They're not just, ready for that or in the mood for that. And that's something that is really paramount when you're conducting experiments in the wild, is that you cannot be naive and imagine, again, that you're just a positivist person, that everybody's going to love your experiment, everybody's going to enjoy what you have prepared for them, and everybody's going to have fun. Really, some people are just going to ignore what you have worked and what you have done, and not participate in any of these potential experimentation that they could do. And then one other thing that we've learned that is also something really important for us is that rather than having a robot that is super reliable, and we need to think about different metrics to understand what the robot is doing and what the robot is actually offering as an experience, rather than just being, as in an industry, a robot that is purely functional and purely reliable. Sometimes the robot is not necessarily perfect. So we have seen some developments of robots, for instance, for the post office or like a delivery, it wasn't a big success. We don't see those robots around so much anymore. In Tokyo, there was the Henna Hotel, which was operated by robots, or the Pepper Parlor. Well, there has been like a lot of hype about it, but what happened is that at some point, the Henna Hotel fired the robot staff because they were terrible at their jobs. They were really sucking at doing what they were supposed to do. They were not reliable. But besides the fact that they said that they fired the robot, actually Henna Hotel still has a robot around, in particular, just to impress people and because this is their signature. So being reliable, being operational and functional is not necessarily a very strong need. And one thing that we found also very important is that teleoperation can enhance robots for services. And there is a very good example here in Tokyo with the Down Cafe, where robots are all operated remotely by handicapped persons and people that are bedridden. And also, as you all know, Gen AI and LLMs can really enhance robot services and provide much better service, but it's not just about being reliable as it was in the past of previous robots applications. So what we have learned is that while Gen AI ambiguity and the myth for predictability are no longer so like Gen AI is useful, ambiguity is important, and the myth of predictability is really a myth. So we don't really need predictability. And there is a very interesting experience that not everyone may have the chance to have like I had, but Professor Ishiguro in his lab at ATR, right next where you are in Kyoto, has developed this new type of systems. It's called it's a robot that basically partly mimic behaviors, but also has some kind of like original random behaviors. And the experience that you have with this robot is very one of the kind. And ambiguity here is not a bug, but it's an ontological feature such that the experience is becoming meaningful again. So again, like imagining that the robot does something while it's not really doing what you imagine, or seeing a bug and thinking that it's something that happens, becomes really paramount for robots for being very diverse and also generating interesting experiences with the users. So in that respect, what we're proposing is a new ethical technical framework that we call the floating ontologies. And the idea is to think about not having the Cartesian fixed ontologies for robot that we have right now. A robot is a non-biological agent. A robot is a non-living agent. A robot is a non-intelligent or intelligent to a certain respect agent. A robot is not a friend. A robot is not a pet, or these kind of things, but rather think about those robots fluctuating between the different places. So a robot can be today a friend, but a robot can be tomorrow a robot or a machine. And the robot could be an entity in between at another point. Depending on the robot morphologies, depending on the experience that you have with that robot, your perception of that robot will really float around this varied possible ontologies. So we want to really break the Cartesian fixed ontologies and go towards these floating ontologies. And for that, our research works on like developing the tools and the methods for understanding like this new floating ontologies, conducting longitudinal fields in the wild, and then continuing the work that we've been doing, and then have possible like tools to understand the experience with the humans, some ethics guidelines, in particular ethics by design guidelines, some synthetic models to understand the robots and to control the robots, and then some safe and expressive robots and avatars. So I would like to like really think, like reliability not like starting from the control perspective, but going to the coexistence. And in coexistence, reliability is different than what it is really in control. And so, for instance, having smart devices that can operate in convenience stores and supermarkets, which are aware of humans and aware of humans' intentions and moods and expressions and engagement. Robots with whom we can go for a walk and that can chat with us, and also using design and in particular participatory design, as we did for our workshops on robots and the city with Monash University back in 2023, where we use mixed reality, participative like workshops to understand what it means for people to have robots around them and how they change their way of living. So for me, robots in the wild is really a mean to understand the robosphere. I mean, robots in the wild is the robosphere, basically, but without the ability to concretely conduct experiments in the wild, I think it will be very difficult to really study the robosphere per se, and in particular in the macro world. So living with robots for me is not just a technical problem, but it's really a cultural and an ontological one. And again, the floating ontologies for me is a way to address that issue. And as a roboticist, as an engineer, I found that philosophy is really a very good way to reframe safety and security in terms of cohabitation, not just in terms of correctness. And for this, I would like to conclude my presentation. I would like to thank you for your attention and all my collaborators, studios, and sponsors. Thank you very much.
Thank you very much, Vinciane. This was great. Any questions? Francesco? Francesco?
I just waving, clapping my hands for the very good presentation. Interesting.
Thank you very much.
Question. Sorry. So you had a question?
No, not in particular.
Yeah, thank you for the presentation. That's interesting to see the kind of diversity of robots in different settings. I just wonder about the use the word experiment many times, but it doesn't seem to be experiments in the sense of having a hypothesis and trying to verify, to check is it falsified in the setting, or it doesn't seem to be about a functional thing so much other than the service robots. For example, when you had the robot in the university corridor, people just walk by.
Yeah.
Why should anybody look at it? It's just kind of a novel object. But if we just rely on novelty, then robots won't be, interesting for very long. I like your idea very much about the flexible ontology, because robots can serve many different functions, and people tend to expect just one type of robot might be the right kind. But so I wonder if you can comment about this, about functionality in context to different types of functionality, and are we just doing kind of art displays and interested in then how people are confused by a robot's presence or a novelty effect, or thanks very much.
No, thank you very much for your question. I absolutely understand. Okay, so maybe I wasn't really clear. I probably didn't say experiment. I said experience quite a bit. So we do some experiments where we have like an hypothesis and we want to test some things. But in the robots in the wild, most of the time, what we want to offer is an experience to people that are interested in taking that opportunity. So in the cafeteria, when you're right, there is the novelty effect. So like students that are going around the cafeteria, they see the robot for the first time, they come and like interact with the robot and take pictures and so on and so forth. And that vanishes over time because, of course, once you have seen it and you know what it does, then you're no longer interested. And that's why I wanted to emphasize the idea that like having a meaningful experience is also very important. If you want people to continue on, then it's probably not so easy to do something too simple is not going to be very like attractive. So we do experiments with hypotheses that we want to test and like participants and so on and so forth in a more like HRI setting. But I really enjoy the experiments in the wild because they really provide insights about things that we will never think about when you write a scenario for an experiment. And that is really interesting because when you write a scenario for an experiment, you don't imagine that your participant is not going to be interested in your experiment. They're coming to do the experiment, so they're going to be doing it. But in the real life, a lot of people are absolutely not interested in robots. They don't care. So that's really interesting to see that, to evidence it, and then to say, okay, if your robot is supposed to help people, then we maybe need a robot that is outgoing, that is going to be able to, reach out to people, to actually for people to see it and to start doing things with it. So that's going to be the part on the experiment. And yeah, in the corridor, yes, again, that's the same, like what I just told you. The novelty effect is absolutely very important, but the more we have experiments in the wild, the more the novelty effect is going to kind of fade, and the more genuine experience we can create with people around, and the more genuine responses we will be able to have with people around.
1 second, there is a follow-up.
Mm-hmm.
Yeah, okay. Thank you for clarifying experience and experiment. I think in French it's the same word, maybe.
Yes, it's true. In French, it's the same word, but I did say experience because I'm careful about picking up the right word when I was talking about it. Anyway.
Yeah, thanks. With the phrase "robots in the wild," the way I've understood it is that not just robots in the wild to provide an experience, but so robots in a kind of unconstrained environment where, for example, it could be a hospital, it could be a school, where any kind of thing could happen. Children could run past, and but it's also if the robot is actually serving a function, like maybe somehow assisting therapy, assisting a therapist. I mean, there are many examples in the literature of those kind of attempts at bringing robots into assistive roles for therapists, for example, or the goals for maybe for medical and for hospital. Those are really those settings are really the wild in the sense that it's not a controlled lab environment, right? So different than just having providing somebody with an interesting experience, but you want to make sure that the robots can function in such a constrained environment in the functional role that's envisaged for them.
Yes, absolutely. And that's why these kind of experiments require a lot of framework on the software and hardware side. And also, as I said, you have to be really fearless about your robots and always expect the unexpected. And that's why working with the kids has been also very, very rich for us in collecting things that you could never imagine would happen. For instance, here, we never told the kids that they can actually hold hands with the robot and dance with it, but they just did it. So, well, that's what happens. And then some of the kids were actually impressed by the robot. They were scared. They didn't want to get close. Or here, they imagined that the robot responds to their behaviors, but it doesn't. So it's all about what is the functionality of the robot if it has to serve a purpose, and then how can it serve this purpose while it's doing this in a very wild environment. Well, that's all the framework that we developed here is really helping on doing this as well. So it's a lot of engineering at the ground, and then after that, releasing the robots outside.
Thank you very much. There is a question on Zoom.
Yes.
Did you see it? So you can answer directly.
Okay, so does computation lead require to see robots less as tools and more as entities on par with humans, not pets, as there would be hierarchy? It seems modern times push the LLM assistance is implicit on the fact that LLMs are obedient tools, implicit ones. Well, I don't think that cohabitation requires any specific rules or hierarchy in the way we're perceiving the robots. Cohabitation could be that some people want to think that the robot is a machine, but sometimes it just goes beyond that. And that's why the flaunting ontologies is really important, is that I don't think that there is a fixed box in which we can classify the robots forever. even a same robot with the same functionality will be perceived differently by two different persons, or even the same person will see the robot as the LLMs are. Like sometimes the LLM is your best friend, and sometimes you hate it for being so knowledgeable and so perfect. So there's always this kind of like very interesting relationships and connections that creates with these virtual entities or like non-biological agents. So yeah, I'm really about like not putting things into boxes. And so maybe cohabitation will be better with people that see it more as a tool. Maybe cohabitation will be better with some people that see it more as a peer. So I don't think I have the answer to that question. I think we'll need to test and everything will happen and anything can happen.
Okay, thank you very much again, Jensian. This was interesting. I think that the philosophers were really very happy of seeing this interest towards philosophy and this elaboration, me included. Thank you so much. And now we have the last talk, Vipra Chopra. I hope I'm pronouncing well your name, Vipra.
Yes, thank you.
Okay, thank you very much. So now is your moment. Do you think you can share the screen?
Yeah.
So the talk is Architecture of Moral Responsibility. We see your slides.
Okay, that's great. So I'm Vipra Chopra, and I want to apologize in advance for my voice because I've been suffering from flu and I have a sore throat, so I'll try to speak as clearly as possible. So my talk is the architecture of moral responsibility, and I'm making a talk about restructuring moral blame to fill the responsibility gap. So first of all, I'll explain what the responsibility gap is. This term was coined by Matthias in 2004, who recognized that there's a gap in responsibility with the advancement of technology and with the co-evolutions of human beings and technology. Technology being technology like artificial agents who have some degree of agency and autonomy, which creates a gap in responsibility of who is to be held responsible in terms of harmful outcomes. So I took the moral framework developed by Gary Watson in his full account of responsibility, and I develop it further in my paper and I apply it to robotic ecosystems to show the complexity of robotic ecosystems, which are multi-agent systems, which include technology, technical norms, and human agents, and also include hundreds of different agents. And a complex system like that needs ethical framework, which is a synthetic framework, which is synthesized according to the complexity of the technological advancements and the changing society that we are living in now. So for a full account of moral responsibility, I argue that we need a synthetic framework which is grounded in human accountability. So I want to clarify that I defend for blaming artificial agents for harmful outcomes, but that does not dilute human accountability, and accountability should always be traced back to human agents and not to any artificial agents or unintended consequences due to any output created by artificial agents. So the first pillar of responsibility is transparent attribution, which is backward-looking diagnostic tool, which helps us trace which human agents are to be held accountable for the harmful outcomes. And the second pillar is accountability, which needs to be realized through robust legal and organizational structures and policies which enforce responsibility and keep it within the human actors. Also, this framework as a pillar of normative clarity, which is forward-looking, since policymakers and are always playing catch-up with harmful outcomes that are coming out of technology. There needs to be a synthetic framework which is also forward-looking, which also takes into account things that can happen in the future with new emerging technologies and already have a framework which can account for them and accommodate it. And here is a chart which basically reinforces that accountability is within the human agents and it needs to be traced back through artificial agents, and I will explain it in more details throughout my presentation. And the ultimate goal is ethical co-evolution within the robotic ecosystem. So I take Gary Watson's account of moral responsibility. In 1996, he wrote a paper called Two Faces of Responsibility, where he recognized that discussions in moral philosophy about responsibility were not distinguishingly in a philosophically meaningful way between attribution and accountability. And he put forth his argument that it is essential to recognize the ethical function of attribution, but also to recognize accountability and attribution as two different dimensions of responsibility. And he defines attributive accountability as something that involves an evaluative judgment, but also has a normative demand along with it, and attributability as an evaluative judgment without a demand for sanction. And about 2 decades later, he wrote Second Thoughts, which was part of an Oxford series on control and agency, as put forth by Gary Watson. And he clarified on his account of moral responsibility, and he clarified on two different aspects of responsibility, which are answerability and culpability. So he differentiated between first person answerability and second person answerability. First person being answerable to yourself, and second person being answerable to other people, and being answerable to moral demands put forth by other people, and also holding other people up to your moral expectations. And he highlighted the social dimension of moral responsibility and the normative function that moral responsibility serves in our society. And he expanded grounds of moral criticism, and he also included negligence and inadvertent culpability, which is an important aspect in artificially intelligent systems and within robotic ecosystems, because unintended consequences should not be written off without anyone being held accountable for them. How I will apply this to robotic ecosystems is because in a philosophically meaningful way, robotic ecosystems and artificial agents within those robotic ecosystems can have functional responsibility. So first of all, Gary Watson says that we do not need complete moral agency to be moral subjects. We can still be moral subjects without being complete moral agents and having complete understanding of agency. And he talks about a form of functional responsibility that corporate institutions have, even though they are not moral agents and they don't have agency or morality, but corporate institutions are liable to legal sanctions because of the social function that they perform and the impact that it has on human lives. So now that we are living in the society where artificially intelligent systems are making life and death decisions which involve human beings, like lethal autonomous weapons used in war, which are currently being used in the Russian-Ukraine war and the Israel war. They are self-driving cars, they are automated policing systems. They are making life and death decisions about human beings, while there are also social robots like conversational AI, which are leading to unintended consequences, which led to 2 suicides of teenagers in the US with ongoing lawsuits. And there is a responsibility gap of who should be held responsible in such a system, multi-agent system, which has hundreds of artificial agents and human agents and technical norms. So I've tried to develop an ethical framework which can be applied to such cases, which will be evolving along with technology. So based on Gary Watson's account of responsibility, I developed 8 sub-dimensions of blame to show the complexity and multi-layered structure of robotic ecosystems and how we can give a full account of responsibility in scenarios which involve human agents as well as artificial agents. So the first sub-dimension is attributive accountability, where blame is warranted because the action both expresses the agent's evaluative commitments and violates shared moral expectations. Then the second subdimension is non-attributive accountability, when an agent may be held accountable without the action necessarily expressing their evaluative commitments. And the third subdimension is accountable attribution, where traits or actions are both attributable to the agent and generate interpersonal demands such as apology or justification. The fourth is non-accountable attribution, where one may evaluate an agent's traits or actions without holding them answer in an obligatory manner. The next is culpable accountability, where the agent is blameworthy for knowingly breaching a moral norm. And the next is non-culpable accountability, where an agent is held accountable despite extenuating circumstances which mitigate their blameworthiness. Then it's a culpable attributability, where a blameworthy act reveals a morally effective aspect of an agent's character. And the final is non-culpable attributability, where an act reflects the agent's self-worth but without grounds for blame. So I developed these sub-dimensions because they can be applied to robotic ecosystems. And next, I give an example of a robotic ecosystem of hardware, which is an example of a lethal autonomous drone used in war, which it's a fictional example that I'm using, which was targeting civilians, and it attacked a civilian building and also ended up killing civilians. So we can see that the sub-dimensions of blame are not mutually exclusive, and they are often overlapping, and they show the complexity which has arisen being in a robotic ecosystem where power and control is distributed within human actors, and it creates a lot of harmful outputs. So as we can see that attributive accountability can be just an example attributed to the senior officer and lead developer. But my point of my paper here is also that we need to have non-accountable attribution and non-countable attributability to the drone, so we can trace exactly which human actors are responsible for the harmful outcomes, and they can be held accountable in a meaningful way, and also which can be included in the technical norm and safety designs for the future designs. And then finally, I give an example of Vetfare of nanobots, which are used in a medical experiment in the example. And it's used to target unhealthy cells, but due to some reason of unintended consequences, they target unhealthy cells and cause internal bleeding and the patient to die. So we can have a full account of responsibility, and we can attribute different subdimensions of blame to different agents, and we can see who is responsible, and which can lead to some form of moral responsibility, which can be applied to this new framework of robotic ecosystems. That's it. Thank you. Sorry, I'm not getting any audio.
Emma, no. Sorry, I didn't open the microphone. I was self-insulting myself. So many thanks for your talk. I see that for the moment we don't have any questions, and we are a bit pushed by the people of the building to leave the building. So we would like to thank you very much, and we will think about it. It was very dense. I would have a lot of questions, but I have to rethink a bit. So who is here and online, we want to say that we will open a special issue, a call for a special issue, together with the people who organize the workshop Mortal Agents, and we will let you know. So we will send you information about that, and of course we will open then the call to everybody. So thank you again very much for participating to the 10th edition of the SBI workshop, and hope to see you soon.